Welcome to an exploration of one of the most intriguing paradoxes in modern data science, the data volume paradox. Here's the paradox. We collect massive amounts of data expecting great insights, yet somehow more data often leads to less real discovery. Let's start by understanding what big data promised us versus what we actually got. The promise was simple and seductive. Collect more data, and you'll gain more knowledge and make better decisions. We thought the path was clear. Scale up from small data to big data, and insight would naturally follow. But reality proved different. As data volume increased, we encountered unexpected problems that actually hindered discovery. Mathematically, we can express this as data volume goes up, but signal-to-noise ratio goes down. Let's explore why more data actually makes it harder to find the truth. First reason. As dataset size grows, the number of possible correlations explodes exponentially. The number of possible correlations between variables equals n times n minus 1 divided by 2, where n is the number of variables. With just 10 variables, you get 45 possible correlations to examine. But with 1,000 variables, you suddenly have nearly 500,000 correlations. This is combinatorial explosion in action. Here's a simple example with 5 variables creating 10 possible connections. Imagine this with thousands of variables. Second reason. With so many correlations, spurious or meaningless correlations start to dominate. The probability of finding at least one false positive equals 1 minus the quantity 1 minus alpha raised to the power m, where m is the number of tests. With a standard significance level of 0.05 and running 100 tests, you have a 99.4% chance of finding at least one false positive. Classic example. Ice cream sales strongly correlate with drowning deaths. Does ice cream cause drowning? Of course not. Both are caused by summer weather. Now let's examine the deeper problem. Big data obscures causal structure behind correlations. True causation flows in one direction, from cause to effect. This is what we actually want to discover. But correlation can exist without causation. A and B might correlate strongly because they're both caused by a hidden third variable. Big data excels at finding correlations, often thousands of them. But causation, the real mechanism, remains hidden in the noise. Correlation is mathematically simple. It's the covariance of x and y divided by the product of their standard deviations. But causation? There's no simple formula. It requires understanding mechanisms, temporal ordering, and controlling confounders. Let's explore another critical problem, the curse of dimensionality. Here's a question. What happens to our data as we add more and more dimensions or features? Answer. Data becomes increasingly sparse. In 2 dimensions, points fill the space. In 3 dimensions and beyond, they spread out dramatically. The volume of a hypercube in d dimensions equals L to the power d, where L is the side length. In 2 dimensions with side length 10, volume is 100. But in 10 dimensions, volume explodes to 10 billion. The same number of data points now occupies vastly more space. The result? Data points become isolated from each other. Real patterns that existed in lower dimensions simply disappear. Let's examine how signal quality degrades as data volume increases. Signal-to-noise ratio equals signal power divided by noise power. This is our key metric for data quality. In small datasets, signal often dominates noise. But as we scale up to big data, noise grows faster than signal. Why does noise grow faster than signal? Several reasons contribute to this phenomenon. First, measurement errors accumulate. Every additional data point brings its own measurement error. Second, more features inevitably mean more irrelevant variables that add noise without adding signal. Third, data quality generally decreases at scale. It's harder to maintain quality when collecting massive datasets. The result, signal-to-noise ratio in big data is often less than in carefully curated small data. Beyond statistical issues, there's a practical computational problem. Massive data requires massive computation. But computational resources aren't the only bottleneck. The real bottleneck is human interpretation. We can compute millions of correlations, but understanding what they mean is another matter. Many algorithms scale as O of n squared or worse, meaning doubling data size quadruples computation time. But interpretation time effectively approaches infinity. No human can meaningfully interpret millions of relationships. This creates an absurd situation. We can compute endlessly but cannot comprehend the results. Big data creates dangerous temptations for what we call p-hacking. P-hacking means testing many different hypotheses on the same data until you find something that appears statistically significant. With big data, you can run thousands of tests. Even if there's no real effect, you'll eventually find something that looks significant by pure chance. Remember, p less than 0.05 occurs by pure chance 1 in 20 times. So with 100 tests, you should expect 5 false positives, even with completely random data. Big data provides endless opportunities to fool yourself into thinking you found something meaningful. Let's examine a famous real-world failure that illustrates this paradox perfectly. Google Flu Trends was launched in 2008, promising to predict flu outbreaks using search data. The promise was compelling. Analyze millions of search queries to predict flu outbreaks faster than traditional methods. Initially, it worked well, correlating strongly with official CDC data on flu prevalence. But then it failed spectacularly, systematically overestimating flu prevalence by 50% or more. Why? The algorithm found correlations between search terms and flu that were actually spurious, driven by media coverage and seasonal patterns. Here's the divergence. The green line shows actual CDC data, while the red line shows Google's predictions increasingly overshooting reality. The lesson is clear. More data, even billions of data points, does not automatically guarantee better predictions or understanding. So when does big data actually work? Under what conditions can we overcome the paradox? First condition, you need strong theoretical guidance. Theory helps you focus on relevant variables and relationships. Theory should guide data analysis, not the other way around. Data without theory is just noise. Second condition, you need clear causal models that specify how variables relate to each other. Third condition, data quality must be maintained even at massive scale, which is extremely difficult. Fourth condition, you must apply proper statistical corrections for multiple testing and confounding variables. One simple correction is the Bonferroni method. Divide your significance level alpha by m, the number of tests. With 100 tests and alpha of 0.05, your corrected threshold becomes 0.0005. Interestingly, we're seeing a renaissance of small, carefully curated datasets. Many researchers now prefer small, carefully curated, high-quality datasets over massive but noisy ones. Sometimes 1,000 carefully chosen examples teach us more than 1 million noisy examples. A quality dataset where every example is verified and meaningful can outperform massive datasets filled with errors and irrelevance. In this context, domain expertise becomes more valuable, not less. Experts can identify which small datasets truly matter. What strategies can we use to overcome the data volume paradox? Strategy 1. Use dimensionality reduction techniques to focus on the most important features. Principal component analysis transforms high-dimensional data X into lower-dimensional data Z, keeping only the most important dimensions. Strategy 2. Apply regularization methods that penalize model complexity. Regularization adds a complexity penalty to the loss function, preventing overfitting to spurious patterns. Strategy 3. Use causal inference frameworks that explicitly model causal relationships, not just correlations. Causal diagrams help us map out how variables actually influence each other, distinguishing direct causation from spurious correlation. Strategy 4. Implement robust validation procedures, including holdout sets and cross-validation. Strategy 5. Pre-register your hypotheses before looking at data, preventing p-hacking and data dredging. Let me give you practical guidelines for working with large datasets. Guideline 1. Always start with a clear, specific question. Don't just collect data hoping to find something interesting. Guideline 2. Deeply understand your measurement process. Know where errors and biases can enter your data. Guideline 3. Extensively visualize your data distributions and relationships before running complex analyses. Simple visualizations often reveal data quality issues and obvious patterns that complex algorithms might miss. Guideline 4. Always test your findings on completely independent data that wasn't used during model development. Guideline 5. Be deeply skeptical of results that seem too good to be true. They usually are. Let's discuss the fundamental interpretation challenge that big data creates. Modern machine learning models trained on big data can be so complex that even their creators cannot explain how they work. This creates the black box problem. Models that can predict accurately but cannot explain why or how. This raises a profound question. Is prediction without understanding truly valuable for science? Accuracy does not equal understanding. A model might predict well but teach us nothing about underlying mechanisms. For true scientific progress, we need both prediction and understanding. Big data often gives us the former without the latter. What does the future hold for dealing with the data volume paradox? Direction 1. Hybrid approaches that combine insights from big data patterns with detailed understanding from small, curated datasets. Direction 2. Development of causal AI systems that learn actual causal mechanisms rather than just correlations. Direction 3. Improved human-AI collaboration, where AI handles computation while humans provide interpretation and theory. The future is collaborative. Humans provide theoretical frameworks, AI does the heavy computational lifting, then humans interpret and refine. Direction 4. Automated quality control systems that maintain data quality even at massive scale. Let's summarize the key lessons about the data volume paradox. Key takeaway 1. More data does not automatically translate to more insight. Quality matters more than quantity. Takeaway 2. As data grows, the explosion of spurious correlations can completely hide true causal relationships. Takeaway 3. Theoretical knowledge and domain expertise become more important with big data, not less. Takeaway 4. Well-curated small datasets can provide better insights than massive but noisy datasets. Takeaway 5. Interpretation and understanding are crucial for making sense of the data volume paradox.